Alright, so this is a starting file we have, and then we have the mass of the rocket is 0.5 kg, gravity is 9.8 newtons per kilogram. And then we can calculate our theoretical velocity and position based on our thrust, and this is the average thrust is what it is supposed to be. And so we have our mass is, where is our mass? 0.05 kg, and g is 9.8 newtons per kilogram, and then our thrust is the average of our thrust. And this is going to be in newtons. We can label some columns, and so we have m, g, and t for our formulas. And then this t is different than this t. This is time. And so our time, we can call this maybe tt, because t is already defined as our thrust. And so we've calculated the average thrust. The theoretical velocity is 0 to 0.8. So this is v theoretical, and say meters per second. And so it's equal to parentheses t minus m times g divided by m times tt. So that's the theoretical velocity from 0 to 0.8. And then our theoretical position is equal to t minus m times g divided by 2 times m times tt squared. So that's the theoretical from 0 to 0.8. And then this is going to be our v0, and this is going to be our y0. So our velocity equals v0 minus g times t minus 0.8. And our position equals y0 plus v0 times t minus tt minus 0.8. And this is minus g divided by 2 times t minus 0.8 squared, except for this is tt, the time. So now we've calculated our velocity and position for all of the times that we want to plot our measured position. And so now we want to plot our measured altitude with 2 different markers, and the theoretical velocity and altitude using lines with time on the y-axis. So this is what we want to plot, and we can go markers and lines. And somehow our V doesn't look right. Oh, because I'm subtracting T rather than TT. Because the velocity should be going downwards because we should be decelerating because of gravity. Now we want our measured position. We actually want two of them. So we want one here for 0 to 0.8, and the other one is 0.8 to 0.7 seconds. So then we can copy this and paste special. Values are in columns and categories are in the first row. And then we can adjust this down. Starting at 1. And if we double click on this, we want these to be no line and maybe a that's border solid line. No. What do we have here? I canceled out of it. So this we wanted to be no line, marker, built-in X, say a red X, and then this one we want no line, marker, maybe pluses. So these are 2, and then we can, this is no marker, and this is also no marker. So this is the theoretical, and then we have to change our labels here. And so we go to select data. We can move this up, and this is, if we edit this, this is under thrust Y, and then this one is after thrust Y. So we have plotted, this is during thrust and after thrust. And then we're going to add a secondary axis for the velocity. So our velocity, and we want that to be on our secondary axis. Add titles including units. And so I'm going to add axis title. This is time in second. Altitude in meter. Velocity in meters per second. we have a legend. And we want to add a second order polynomial trend line to the experimental altitude after thrust using a dashed line. So we can right click, add trend line, a second order polynomial, and then we want to display the equation and r squared. And then we probably want to make this go just to 7 seconds. And then we also want to do our curve fit parameters using linist. And so it's linist. The known y's are here. Then the known x's are your time. And that's what we want to do is power of 1, 2 to get the second order curve fit. And then Control-Shift-Enter. That gives us your parameter here. What I should have done is all of these together, Control-Shift-Enter. So that gives you your three parameters here are these three parameters here. Oops, it doesn't quite match. We don't want our trend line, we want our after thrust. So this one I didn't go all the way to 0.8. So now it matches perfectly. So the altitude sensor is plus or minus 5 meters. We want to add that to the experimental data. So we have here, we want to add error bars. And then we want to have a fixed value of 5. And then if we select the X error bars, we can delete those. Similarly here, we can't do it that way. We can add error bars. And then we can select R, X error bars, delete, select Y error bars, and these are going to have a fixed value of 5 as well. So we want to move our legend overlapping the chart. Let's make our chart a little bigger. And maybe doing this on the right. And right there. And then the magnitude of the acceleration is twice that, so it equals absolute value of that times 2. So it's 10.13. G equals 10.13. So that is the first one. Second one, what we need to do is add a new sheet. So we added a new sheet. And then we have an equation for based on x. And so we want x to start at -2, step size of 0.1. So it's equals that minus plus 0.1. We can drag this down to, no we can't, we just want to drag this one down. This is our formula. All the way down to 2. And then we have y1 and y2. So this is x. And if we label it, then we just have equals absolute value of x to the power of 0.8 plus the square root of 4 minus x squared. And the other one is similar, except it's a minus. So we can copy those down. And then we can insert a line chart. And we go down to 2. And so we can make this going from -2 to 2. And the vertical, we can start at -2 as well. And maybe this is 1.9999999. Now it's happy. So we have love in equation form. Lastly, we have simultaneous equations. And so you basically set up your A matrix. So it's 3 minus 1, 2, 1, 0, 4, 4 minus 2 minus 4. And then your C matrix is your coefficients on the other side. So it's 7, 4, negative 12. And then you have A inverse. And so again, matrix operations, you need to decide. So this is now M inverse of your A. And then Control Shift Enter. What's wrong? 3 minus 1, 2, 1, 0. So this is 1. There we go. 4 minus 2, 1. And then this we do equals M molt of the inverse of A and C. Control Shift Enter. So this is A, B, and C. So that's the answer.